Okay, now let's take a look at an exercise involving rotational kinematics. And the way we approach rotational kinematics is really pretty much exactly the same way that we approach linear kinematics. When we're first learning to do these, I think one of the easiest things to do is just see what the problem would look like if it were a linear kinematics problem instead of a rotational kinematics problem. So let's take this one where we have this turntable spinning around that then the power is turned off and it comes to rest. Let's kind of rewrite this in terms of linear quantities. So instead of a power being turned off to a turntable, let's say that we have a car that's initially traveling 78 meters per second. So let's say something like a car traveling 78 meters per second, something like this. And then we find that it takes 10 and a half, we'll just say 10 and a half meters for it to stop while slowing down at a uniform rate. So we have this is key, right? So a uniform rate, a constant acceleration. So that's when we can use those rotational kinematics equations, just like when we could use the linear kinematic equations. And we want to know what is the angular acceleration. So really, doing this in linear, we could just say what is the acceleration in meters per second squared of the car, right? And how long does it take to stop after the power turned off? Well, time is time. And so if we had, this car traveling 78 meters per second, hits the brakes, takes 10 and a half meters to come to rest, then what's the acceleration? How long does it take? The way we would set this up in linear terms, we would say here, all right, I have my given. What's given to us here, we have the initial velocity is equal to 78 meters per second. The final velocity, since it comes to rest, v final, this is equal to 0 meters per second. And we know that it takes 10 and a half meters to come to rest, so delta x is equal to 10.5 meters, right? And we're asked to find the acceleration and how long it takes to stop. So how much time it takes to stop. So because obviously we're given the distance it takes to stop already, right? So acceleration and the time to stop. And then the solution, what we would look for is we would say, all right, I need a kinematic equation. There's two parts to this, right? There's A and B. A is for the acceleration, B is for the time. And I have so I'm going to come up with two different kinematic equations. For part A, I need a kinematic equation that has starting velocity, final velocity, displacement, and acceleration, right? And so then I can, writing all these out here, I need an equation V naught, V final, delta x, and A. And, I can use this V naught squared, V squared equals V naught squared plus 2 ax delta x, right? That's what I use for the first part. And then that's for part A. And then for part B, we would need something that has, starting velocity, final velocity, displacement, and time. So for that one, I could use delta x equals v naught x plus vx over 2, our average velocity, times time. And I can solve this for time, right? That would be their strategy. And so it's the same thing with rotational kinematics. But instead of traveling at 78 meters per second, it is traveling at 78 revolutions per minute. And I want to get to radians, so there is one extra little step here. I need to make sure that my units are in radians. You can't actually do it in revolutions per minute, but then our acceleration would need to be in revolutions per minute squared, and that's just a weird unit. So, and this v naught, instead of this v naught, it would be omega naught, right? We convert everything to Greek for rotational motion. So omega naught is equal to 78 radians per second. Then I multiply by 60. Oops, where am I? I'm so sorry, it's not radians per second, it was revolutions per minute. Revolutions per minute, RPM, revolutions per minute, right? And then multiply by 2 pi radians per revolution, and multiply by 1 minute per 60 seconds. And make sure everything cancels out. Make sure I set that up correctly, right? Revolutions cancel out, and we have minutes cancel out, and I'll be left with radians per second. And so this comes out to omega naught. Let me write this, actually, maybe I'll just write everything in blue here. Omega naught is equal to 8.168 radians per second. And then instead of a V final, it's an omega final, right? Omega final is equal to 0 meters per second, but it's not actually meters per second. It would be radians per second, and obviously converting 0 revolutions per minute to radians per second is just going to be 0 radians per second. And instead of delta x, instead of a linear displacement, it becomes an angular displacement, right? So a delta theta. And this is equal to 10.5, what does it say up here? It says revolutions. So another little conversion that we need to go through. We need to convert radians or revolutions to radians, right? So 10.5 revolutions times 2 pi radians per revolution. And the revolutions cancel out. And we have here 21 pi. Right, that's 21 pi radians. So delta theta is 21 pi 21 times 3.1415. We'll call it, it comes out to about 65.97 radians. That's delta theta. And then instead of finding linear acceleration, we are finding angular acceleration alpha and time, which time stays t, still t. And then, so the solution, now we're looking for something with omega naught, omega final, delta theta, and alpha in it, which is the same exact equation here. Becomes omega squared equals omega naught squared plus 2 alpha delta theta. And, right, so then alpha is equal to omega squared minus omega naught squared over 2 delta theta. This is equal to 0 squared minus, we have for omega naught 8.168 over 2 times 21 pi. And alpha comes out to be negative 0.506 radians per second or radians per second squared. And there's the answer for part A. Same method that we would use with linear motion, linear kinematics. And then for part B, again, instead of looking for an equation with V naught, VF, delta x and t, it has omega naught, omega final, delta theta and t. So that's this one here. This is delta theta is equal to omega naught plus omega final. I don't need to put x and y subscripts with omega because it's either just clockwise or counterclockwise, right? So it's positive or negative. So I guess that's kind of nice. Maybe rotational kinematics gets a little bit easier because then we don't, you don't do projectile motion with it. So although we could have something spinning and in projectile motion and rotating at the same time, I guess. But then still we would treat it all independently. So we're just plugging in here. We have delta theta was 21. Oops. 21 pi is equal to 8.168 plus 0 over 2 times time. We have time is equal to 2 times 21 pi over 8.168. And so the time comes out to be 16.2 seconds. And you know, just like we have with linear kinematics, for part B, we could have also used, we could also use here omega is equal to omega naught plus alpha t, right? Or this is like v equals v naught plus at. It's the same kinematic equation there. And then solve for time that way. But of course, if we had the incorrect alpha, then we would get the incorrect time, right? So it's good to use this equation here instead. But this is, we can just use this as a check, right, to make sure there wasn't any mistakes there. So really, yeah, rotational kinematics isn't really that new. We just have to get used to converting to radians per second squared, and kind of get used to some of the Greek variables.